Welcome to this lecture about air humidity. Air humidity impacts strongly thermal comfort. Maybe you remember that we called the air temperature the dry bulb temperature. There is generally some water vapor contained in the air, and this vapor can condensate under certain conditions. The dry bulb temperature measured by the thermometer on the left is the temperature of the air when there is no condensation of water. This is just air without fog. As you probably already know, air is a mixture of different gases. In mass percentages, 78% nitrogen, a bit less than 21% oxygen, 0.9% argon, 0.03% carbon dioxide. These percentages are for dry air, but as we just said, air also may contain water vapor up to around 8%. In that case, of course, all percentages change accordingly. The mass percentage of water vapor in the air depends a lot on the weather and the surroundings. Is it rainy? Is there a lot of vegetation? Is it warm or cold? Maybe you are wondering how it is possible to have water vapor in air while you have learned that water under atmospheric pressure vaporizes at 100 degrees Celsius, as you can see on the curve on the right. Well, this is quite simple. Let's take a volume of air at atmospheric pressure, 1 bar. If this is pure dry air, the pressure of the air is 1 bar. If it is mixed with water vapor, this water vapor takes a certain place in the volume, and this is reflected in what we call the partial pressure. The less water vapor, the lower its partial pressure, and the higher the one of the air, because both should sum up to 1, the atmospheric pressure. The water in a mixture of air and water vapor has a very low pressure because, as we will see later, the quantity of water vapor is always very, very small. The pressure of water is far below 1, and according to the boiling curve of water on the right, water will therefore boil and condensate at very low temperatures. For instance, at the pressure of 0.024 bar, evaporation and condensation will take place at 20 degrees. The maximum quantity of water vapor that can be absorbed by air depends on its temperature and pressure. At atmospheric pressure, it therefore depends only on the temperature. In the graphic, you can see on the horizontal axis the maximum water vapor content in gram water per kilogram dry air, and on the vertical axis the air temperature, the dry bulb temperature. For instance, 1 kilogram of air at 0 degree can contain a maximum of 3.8 gram water. The air is said to be saturated at this water content, meaning that droplets of water start to appear and no more vapor can be absorbed. At 20 degrees, 1 kilogram of air can absorb a maximum of 15 gram water, and at 14 degrees it is 49.1. The humidity expressed in gram per kilogram dry air is said to be the absolute humidity. In other words, each temperature corresponds to a specific maximum content of water in the air. If the content is below this maximum, water will be in vapor form. If the content is equal to this maximum, no more water can be absorbed and the water vapor starts condensing. Let's take again the example of a water content of 15 gram per kilogram dry air. The corresponding boiling temperature is 20 degrees. If the temperature is higher than 20, the water is in vapor form. If it is below, water condensates. Conversely, at 20 degrees, air cannot never hold more water than 15 grams per kilogram. With 15 grams per kilogram, the air is totally saturated, cannot accommodate any more water vapor. It is said to be 100% humid. Any more water being brought into the air will remain liquid. That is what we observe when there is fog. See picture left above, or when indoor air is cooled down by flowing along a cold window. See picture below. The temperature becomes lower than the boiling temperature corresponding to the water contents. The blue curve on the diagram is called the saturation line. Observe carefully this curve and note that the higher the air temperature, the more water vapor it can contain. At low temperatures, it can contain almost no water vapor. Also note that even at high temperatures, the maximum quantity of water vapor remains very low in mass. The maximum on the x-axis is 87 gram water per kilogram air, corresponding to a temperature of 50 degrees. It is saturated and therefore 100% humid, but still the water content is only 0.087 kilogram water, which is a mass percentage of only 8.7%. At 20 degrees, the mass percentage is only 1.5%. Now that you know what is 100% humidity, let's go a bit further. The water vapor content on the x-axis is also called absolute humidity or humidity ratio in the US. The term ratio may be a bit confusing, so in this course we will just use the term absolute humidity. This absolute humidity does not tell anything about the feeling of humidity. The perception of humidity relates to how far the actual conditions are from the saturation line. An absolute humidity of 15 grams per kilogram dry air will be experienced as extremely humid at 20 degrees Celsius because it is on the saturation line. If you are then doing your gym and sweat a lot, it cannot evaporate in the air and your body will remain wet. It will feel extremely humid. Opposite to this, if the temperature is 30 degrees, the state is far from saturation. The sweat is vaporized in the air and it does not feel that humid. If the temperature range we are dealing with, the water vapor content varies almost linearly with the partial pressure of water. So, the x-axis can be represented also as partial pressure, like that. As said before, it is almost linear, but not completely. The exact definition of relative humidity is that it is 100 times the partial water vapor divided by the saturated pressure at that temperature. In this picture, the partial vapor pressure in point A is 2.3. The partial vapor pressure on the saturation line at 30 degrees is 4.2. The relative humidity of the air in point A is therefore 100 times 2.3 divided by 4.2, which is 54.8%, 55% when rounded. Note that using the mass ratio instead of the pressure ratio is wrong, as it has no physical basis. The pressure ratio is equal to the mole fraction, not to the mass fraction. However, working with the mass ratios will give a very reasonable approximation in the temperature range considered. For point A, using the mass ratio would lead to 15 divided by 27.5, which is 54.5%, also 55% when rounded. Let's go further with this example. When do we feel a humidity of 50%? That is when, for a certain temperature, the humidity is just in the middle between dry air, which is zero humidity, and a 100% line, looking at the partial pressure scale. So, at -10, it will be here, at 0 here, 10 degrees here, and so on, by which we now have drawn the line of 50% relative humidity. We can draw such a line for each wanted relative humidity. I drew it here for 80% and 20%. By the way, such a diagram is known as Mollier diagram for humid air. In a large part of the world, it is known as the psychrometric card. The psychrometric card is just the Mollier diagram flipped horizontally, like that. So, what happens if air at 30 degrees with 80% humidity flows along a wall at 26 degrees? On the surface of the wall, the air temperature is 26.2, so the water vapor would already start condensing on the wall. We say that the dew point temperature is 26 degrees. If the humidity is 50% instead of 80%, condensation will start only if the wall has a temperature below 18 degrees. We say that the dew point temperature is 18 degrees. For a comfortable and healthy environment, it is recommended to keep the humidity between 30 and 70%. If the indoor temperature is high, the body needs to release heat by sweating, which becomes very difficult at a high relative humidity. If the relative humidity is 100%, the air cannot absorb any water vapor, the skin becomes wet and less heat is lost by transpiration. If there is no ventilation or air treatment, the humidity in an occupied building will always be higher than outdoor, because people always release humidity by sweating and also purely by water diffusion from skin and by breathing. That is one of the reasons why large amount of ventilation air is needed in buildings. A humidity above 70% is not wishful. Not only is it very uncomfortable, but it may then happen that the water vapor condensates on cold surfaces. Moisture on walls or window frames damages the structure. It can rust. It also endangers the conservation of paintings or books, for instance, in museums. It is favorable to the growth of molds and fungi, which are damageable for health. And last but not least, it makes the air being perceived as damp and stuffy and can worsen respiratory diseases. That is why an upper limit of 70% is preferable. The lower limit, at around 30%, has more to do with avoiding electrostatic shocks than to do with real burden coming from dry air. In general, when people complain about too dry air, the complaints relate to particulate matter in the air or to a combination of particulate matter, draft and poor lighting causing irritation of eyes or throat. It seldom relates to the low relative humidity itself. Let's say that in general, people experience dusty air as being dry, also when it is not. This figure shows the relationship between comfortable air temperatures and relative humidity. For instance, at an air temperature of 24 degrees and a relative humidity of 35, people would feel just comfortable. If the relative humidity increases above 65%, most people will start feeling very uncomfortable. If the air temperature is 20 degrees, a relative humidity up to 70% will be comfortable, and discomfort will arise only from 80% relative humidity. We made clear that hot and humid air hinders the process of sweating, which is essential for thermoregulation. But what happens in cold and humid air? Well, one could think by analogy that cold humid air would feel warmer than cold dry air, as less sweating takes place. But the opposite is true. In cold air, we do not need sweating, and we feel colder when the air is humid. This has to do with clothing. The fibers in clothing absorb humidity quite well, even if we don't see it and they don't get really wet. The more water in clothing, the higher its thermal conductivity, by which heat transfer to outside will increase and we will feel colder. Last but not least, be aware that both humidification and dehumidification of air costs a lot of energy. When humidification is needed, one should then humidify to the lowest possible acceptable humidity. When the air is too humid and dehumidification is needed, one should then dehumidify to the highest possible acceptable humidity. This way, a minimum of energy will be consumed. This will be treated in detail in another MOOC. To recap this lecture, what you should remember about humid air is that there is a maximum to the possible water vapor content of air. This maximum moisture content varies with temperature. The higher the temperature, the more water air can contain. At maximum moisture content, the air is said to be saturated. The absolute humidity of air is the amount of grams water per kilograms dry air. The relative humidity expresses how far air is from the saturation line in terms of pressure ratio. Humans are receptive to the relative humidity and not to the absolute one. If humid air is cooled down, condensation will take place from the moment the temperature is below the corresponding saturation temperature, which is called the dew point temperature. A comfortable humidity range is considered to be between 30 and 70%. Above 70%, the air is close to saturation and it is difficult for the air to absorb the humidity from the body. At warm temperatures, people will feel too warm and sweating will be hindered. Low humidity levels are much less problematic. Finally, be aware that humidity control costs a lot of energy. Thank you for listening to this lecture.